We're the Alabama football team. I'm Austin Otto.
I'm Nick. I'm Mike.
I'm Mitch.
We're working on a project of creating a AI system for a foosball table that has already been created by 2 previous teams working from the IME department. Our current overview or seer of this project is Dr. Macedo, the chair of the IME department. And we're also sponsored by Yasukawa from Motors, who are graciously provided us with 8 different servos, which are used to control the people on the table for the opponent side. One side is the computer, which we are developing the AI for, and the other side is a human player. You can see that this side is human, while the other side is computer. We are also, the table was given us to as a deal by Warrior Table, and they gave us it for a relatively cheaper price than usually would go for. And the camera that we are using to capture and track the ball is by Cognex. Using the language that Yasukawa has for the motors, we are developing the AI for the table, in which we have to create multiple different AI levels for. We are to not just make it so it can be playable against, which it currently is, though not very fluently or well. Our goal is to increase that so it can beat almost anyone, professional or not. But we're not trying to make it just so it can beat everyone. We also want to make it so it can play against intermediate and casual players as well. Because we don't want everyone to just have it beat you all the time. It would be not fun and be very frustrating. Things like that. But the reason why we have this project isn't just as a little fun little game. We're doing it so we can show the use of the servos and show the work of Cal Poly students and teachers. As you see, this is currently how it's set up. It's through a plain glass, which you can see the servos and the drivers. The servos are these little motors. You can't really see them up here, and the drivers right here, which, since it's in a plain glass, you can see and how fast they function and how precise they are when they move. Our marketing requirements are that it's user friendly. It can be easily accessed, easily started up, easily played. It has multiple levels of difficulty. As I've mentioned before, we want not just to beat everyone, and we also want it so it's very very smart in what it does, not just hitting a ball all the time.
Okay, as far as engineering requirements, our job is mostly to design the AI that will obviously score more reliably than the existing system does already. Currently, the system's not very good. It honestly just moves towards the ball and just tries to hit it, and a lot of times it just misses it. As well as we need to create multiple levels of difficulty. The idea between that is so that this table can be used as either a fun, reliable play opponent, or as like a training device. We don't want it to be able to not necessarily beat everybody, but be a challenge and fun for everybody to play. Ultimately, the product will be taken to trade shows to try to show off the accuracy and precision of the motors and controllers that Yasukawa has provided for us. To accomplish our goals of creating that, we find that we needed to improve how the ball is tracked, because currently there is a wide area underneath the other players that the camera cannot detect where the ball is located. So in order to actually create that AI, we found that we needed to change how we track the ball in order to make that more reliable. Another engineering requirement, we need to ensure that whenever people wanted to like examine the motors, or even when they open the encasing, that they don't actually get hurt by motors that are just moving around quickly and yeah.
Alright, so on to the system architecture. Like we said earlier, we inherited this project from previous groups, so most of the hardware and basically the system implementation we're kind of hands-off on. Coming in though, it was kind of hard to take a picture showing the entire system because of its size, but here we have the camera that is overhead of the table. We have the table enclosure, servos for rotating the rods, servos for moving the rods, the 8 drivers, 1 per servo, the control unit, and over there we have the computer that uploads the code we developed onto the control unit. But coming into this project, it all already works. It's able to run the code that they developed prior, like we said earlier, without brains, but it's able to play against you and just kick when it's within kick threshold, basically. But that's what we're coming in with, and the only changes that we're going to need to make from at the system level is, as you can kind of see here, it's much darker in the middle because right now the lighting is on the border of the table, and because our camera only sees in black and white, so it's only seeing things based like on the saturation, how dark or light it is. There's parts on the table where the ball is inconsistent as it travels down, and it'll start picking up reflection on the tape, and so we are planning on implementing lights overhead, just like the camera, to counteract the dark spot in the middle and try to have more consistent lighting throughout. Another thing we have to implement into the system is a UI, which we're planning on using potentially a Raspberry Pi with an LCD. That this UI would allow the players to change the difficulty, pause the game, start a game, be able to change the settings even during the game to restart or before the game in order to play the most even possible foosball game against the computer. And then going on to the mechanical design.
As far as mechanical design, as Mitch has already mentioned, this was all done for us. We have the foosball table on one side, which has a covering plexiglass sheet that can move up and down depending on what we need. That's mostly for safety. On the other side, we have another plexiglass casing which encases the motors and the controllers and others and such. And then there's also the camera that is facing down. That sends basic location data of the ball to our controller. This is a view from the motor side. These are all the motor drivers, and right here is also a controller that is used to send data to those controllers or those drivers. This is just another view. We have lots of these. Yeah, go for it. This is a very basic black box diagram of what our hardware actually does. On the far left, you can see the camera runs computer vision code that is run on a CPU dedicated to camera and computer vision techniques. That sends basic vision data to our controller, which takes that data and runs the code that we write and distributes tasks to the motor drivers, which just drive the circular motors. This is the controller, and the drivers. Go for it. And these are the servos that are connected that control the translational position of the rods. And then these are the servos that control the rotational position of the rod. And then there's also the camera, which might help out.
Alright, so starting on this project, a huge thing to tackle is the camera. Because unfortunately, we ran into problems where the camera would lose the ball, the table wouldn't really know where it was, and it would freeze. And if you're playing foosball against somebody, you know, they're not going to stop playing once the ball gets underneath one of their people. And so the first task that we're looking to conquer is the vision problem. Next slide. So this is what the camera is seeing. Right now we have the lines on the table actually taped with electrical tape because the way the program was running, it's looking for patterns. And so basically we told it, like, this is what the ball looks like, and give us the XY position in this general square of where the ball is. And the problem was that if the ball was in certain areas, like the center here, where there was like actually a big soccer ball decal, it would lose the ball entirely because of the other kind of noisy patterns going on around it, as well as the lines and even a small white dot that looked a lot like a foosball. So as a temporary solution, we taped down the lines and made sure that it was seeing the ball most of the time. Next slide. So this machine vision software is through a program called Insight Explorer, which is developed with the Cognex camera. And what we're doing right now is we're searching for patterns and of the ball and just setting XY coordinates, and all that is computed in the Cognex camera and has a dedicated CPU. What we want to be doing in the future is not only looking for patterns, but also looking for blobs, so to speak, which would be a small chunk of light-colored object, so that if the ball is partially occluded, go to the next slide, partially occluded like this, we imagine this is kind of the feet of a foosball player up at a horizontal angle. One problem we run into is that although this is a perfect place for a guy to kick, it doesn't know that this circle is the one it's looking for because of this extra noise in it. And so what we want to do is be able to not only look for this circular pattern, but also for a blob of a general size that would be this color. So that instead of just seeing the full ball, we could look for partial balls, also do different things with how we're tracking it. The second part of what we're doing for the vision is creating kind of a memory bank. So what the Cognex camera does is it sends an X and a Y coordinate as quickly as it can, or as quickly as it takes images, to our main CPU, and we kind of have to work off that. And the problem with that is, if it loses it, it stops sending data, or it'll send data that doesn't make any sense. And so what we're planning on doing is implementing kind of an array of previous points that we know the ball was, and using kinematics to kind of guess where it might be, as a second line of defense for an actual reading. So in the case that we don't know where the ball is exactly, or the camera can't see it and know where it is, we have a pretty good idea of where it might be. And so we can move rods around, we can have it try different areas and do different things that might free up the ball to be seen and then acted on.
Okay, so coming into the software architecture, to be able to understand some of the design decisions we made, I'm just going to quickly go over the environment and how you actually program this control unit. So for our project, we are using the Yakuzawa IEC 61131 programming environment, and we are using their MotionWorks IEC2 Pro IDE. So the main ways that you program in this environment are with function blocks, and as you can see here, so it makes it really easy to visualize, because it's done for you, what states are running, what state will be next as it progresses, and makes it really easy to manage. The code, or the libraries that Yakuzawa has for the control units, they come in tiny function blocks. Some of these function blocks, yeah, like these function blocks are very specific and talk directly to the hardware, so we don't actually have to implement those. We just have to basically map our abstraction of the goalie rod to rod 1, and then we can use their function blocks to do all the physical moving of it. And then besides the function block diagrams, if you want to make your own to do something more specific, you have to create your own, and inside them you use structured text. And so it looks a lot like C syntactically. It's not really, actually, it's pretty ugly. It's pretty hard to understand, to come in and get a grasp on initially, but using their code as an example, we were able to pick it up and slowly make changes to become more readable and usable. Okay, so yeah, coming in this project, just like how we inherited the system, we also inherited code. However, they were not as software savvy as we are, so and they were much more crunched on time. So the logic that they were able to implement is very, very basic. The main blocks that we were able to salvage from their code is kick, and being able to tell how hard to try to kick, and so that you can try to avoid torquing out if the ball's there and it just tries to spin too hard but is incapable of spinning. A block that is able to control the rotational angle of all the players just by passing a degree. It's able to know where it is and how to change to get to that angle. And then a block for covering. One of the blocks that we have from them, you just have to give it a coordinate and it knows exactly how to move the rod to make a player cover that zone. So they've saved locations of each player on the rod and know how to move the rod appropriately for a player to cover a specific position. So coming down to the software, I'm going to go high level to lower level. These are the main states of the system. There's the initialization, which checks all the hardware. It'll check the drivers, making sure nothing's aired out. And if everything passes that, then we go directly into the pause state, which it'll wait for the UI to say start a new, or set the settings of a game, and then prior to the game beginning. When the game is online, you are able to pause the game once again through that UI, or if the lid is open that covers the servos and all the hardware, it immediately will, an interrupt is thrown and it'll immediately jump to pause and disable all the rods to prevent someone from reaching in and getting hurt or damaging the hardware while it's active. And then going down into the online, when it's in online, there's also some states. These are more specific to playing foosball. So initially it goes into a kickoff state, which the system will wait until the ball enters from the area where you toss it in at the midfield out on the side where the lid opens. You wait for the ball to enter play from there before the rods will actually start moving and playing. So once again, if someone reaches in, the camera won't. If they reach in, well, I guess if they reach in from where the ball should be played, it might detect it as a ball. But now we'll be able to prevent scenarios where someone like just reaches over, they detect the ball when it's not active and start kicking and doing random stuff. So once the ball enters play, we go from the kickoff and we start playing. If the lid is ever opened to the table to move a ball, because the ball's, once again, if the ball gets stuck under a player, we lose vision of it, and so nothing happens and you have to reach in. And so what we've been using is a spray can so you don't get kicked, or a stick, but the stick got snapped because we didn't move the ball and now the ball's seen, so let's kick it. And then
The motors are not friendly.
yeah, very strong, very, very strong motors, and that's why they work out too. But anyway, so when the lid is open, we immediately go to a timeout, and you stay in the timeout until the lid is closed, and then you continue playing. We also want to incorporate, this is going to be more challenging and a reach goal, is being able to detect when the ball is lost in vision going into the goal, so that then we could then go to the kickoff state. However, the ball most of the time when it's scored goes too fast that we don't have enough frames of where it was going to know that it went in the goal specifically. So we're still trying to work on that, but in the end, that's the idea, is that it'll pause on its own and wait once again for the ball to come into play from the right spot. Okay, so even lower level, how we're implementing the strategy. Coming into the project, they had blocks for the X position logic and Y position logic, totally separate, that controlled all the rods. We wanted to make it a little more organized, a little more readable, and make it easier for us to implement the strategies that we've been discussing. So this is the large controller, the coach of the team. The coach is informed of all the players' states, and he's also informed of the ball's position from the camera, the XY coordinates we get. The coach analyzes what all the players are trying to do, the present position of the ball, and he also, internally he stores the array, where the ball's been traveling, so that he can then predict, try to give an accurate prediction to the players as to where the ball will be when it reaches them, and also tells them what formation to play in. In this case, it would be defense, offense, clear the ball, so that he's able to inform all the players of a common formation so that they can act together rather than separately. So for each player, a player is for each rod. We have the goalie rod, defender, midfield, and forward. The player is going to take in the formation from the coach so that they all can know what each other are doing. He's going to take in the ball position, the ball predicted decision, And with all this information, specific to each rod, the goalie will act differently than the defender and so on. The player will then decide which skill it should be executing. If the ball is near them and they're in an offensive, but they want to move the ball upfield, then it will pass. If the ball is downfield but we have possession, it will try to catch the pass, or clear, shoot, possession, otherwise. So, as the player gets all the information from the coach and the ball position, the player is then able to select which state to execute, which one to go into. It executes appropriately, and then it will inform the coach of which state it executed, if it was successful, and so on, so that the coach can then change the formation or inform the other players to act appropriately.
Alright, so in conclusion, we're really excited about this project. It's a fun thing to do, and it's fun to be going and doing foosball, and at the same time, we're all very excited to be working on an artificial intelligence system that is relatable, and people really understand what's going on the top level. In the future, we hope to be really refining the AI and making it so that everybody can play against this table at the skill level that from beginners all the way up to hopefully maybe more of a professional level. We will always be needing testers, so if anybody wants to come by the Bonnerson route, we've got an automatic foosball table that's waiting to be beaten. So come by. Does anybody have any questions?
So you're using the camera to track the ball. Is there any reason to, or any reason why you haven't maybe tracked the opposing players, and maybe have a blocking strategy if you're missing the ball, or is there a reason that the ball is the only input to the system?
The difficulty with tracking a lot of different things is speed, and so if we wanted to, we could probably we have kind of two options of tracking other players. The first one being having multiple cameras, and having multiple cameras that would all be computing separate things like where this specific player is. While that's definitely feasible, it is also extremely expensive because this camera is in the thousands of dollars range, as well as the motors, and so we don't have the funds necessarily. We don't want to be asking for 4 more cameras. A second option would be a sensor, kind of sensing where the rods are themselves, and we decided that we didn't want to quite go that route until we have a better handle on the table's operation on its own. We feel like tracking the opponent is going to be more of a higher level strategy than we are at right now, and so we're kind of taking the baby steps to get to that point before we start thinking about things like
How many FPS is the camera?
It depends on what we were using, because you can change how the image is being filtered, what we're looking for, like this pattern, that pattern, shape. So it really depends, and it's actually really cool. The software we've been using will tell you as you apply the filters and look for certain patterns. It'll tell you how long that computation takes, so that then we can see what kind of frame rate we would get depending on which filters or what we use. But right now, it's like 20.
Right now we're about 25, and we're hoping to optimize that further so that we can get more frames per second. But yeah, right now 25, 30 is kind of the range we're looking at. Hopefully more towards the 40, 50, 60 range eventually.
Are you imposing limits on the AI that would mimic a human player, like the 2 hands at a time kind of rule?
We've talked about this, and in some sense it would make it more of a human-like player. On the other hand, humans do a lot of things that would be extremely difficult to implement in this system, just because we inherently are much more fluid and subtle than the machine can be on an easy scale. And so we've decided not to go that route, at least for the higher levels. We may end up implementing it for a beginner level, because we have to kind of create artificial difficulty somehow. Is that we won't, unless we spent years and had teams working on this thing, it would be very difficult for us to ever reach the level of a professional player. And
couldn't you just oscillate the goalie at like 100 hertz or something?
we could.
You can make it impossible, but
we felt that having all 4 rods operating at one time would feel more fair than having the goalie and the defenders, moving so fast you actually can't see them. But so it's kind of creating artificial difficulty in a sense, just because this player isn't as capable as a professional player would be of very subtle, passing and movements that are more kind of, as we understand them, feel rather than pure strategy.
Your test plan is going to be awesome, I can tell. 40 hours of foosball.
Any other questions? All right, thank you very much.